the topic of this mini course is about understanding dualizability in low-dimensional higher category theory, and in particular how this dualizability structure gives you a rich connection between topology and algebraic structures. So last time we spent most of the time talking about higher categories and what those were supposed to be. And so today we're going to switch a little bit and talk about dualizability and what that is supposed to encompass, and from the structure that you get out of things with this higher categories with this dualizability structure. So the most fundamental basic part of dualizability, example of dualizability, is about duals in two categories. So, definition. A morphism, a one morphism in a two category is left dualizable if there exists a morphism G going the other way and morphisms, the evaluation, which goes from the composite FG to the identity on Y, and the co-evaluation going from the identity on X to the composite the other way, satisfying two equations. So you can start with the morphism F, and you can apply the co-evaluation. You can think of F as being first composing with the identity on X and then applying F. So then you can apply the co-evaluation to get FGF. Then you can apply the evaluation to get back to F. And this composite should be the same thing as the identity on the morphism F. So this is some two morphism in our two category, and this composite should be the identity on F. And there's a similar one. If you start with G, then you can apply the co-evaluation to get GFG, and then you can apply the evaluation to get back to G. And this composite should be the identity on G. So there's something you should always do when you introduce this kind of a notion, which is to draw a string diagram sort of explaining some of the geometry that is involved in these equations.
I'm sorry, but could you explain a little bit more what that means when you write the evaluation being FG2 identity 1, 1?
Right, so G is a morphism. So this is taking place inside a two category. So sorry, the question was, can I explain a little bit more about the evaluation and what that means? So this is taking place in a two category. So we have some object X, and we can apply, and we have an object Y. And so for example, we can apply the morphism G, which goes from Y to X. That's a morphism in our two category. And we can apply another morphism F to get to Y. So the composite of first doing G, then doing F is FG. And it's backwards because our function composition is written backwards. So maybe I can fix that by drawing my arrows backwards. Okay, then it sort of matches. So this composite is some morphism which goes from Y to Y. There's another morphism which goes from Y to Y, which is the identity 2 morphism on Y. And I can ask for a map the evaluation.
That's just the identity one morphism.
That's the identity one morphism. Thank you. Yeah. And the evaluation is a two morphism from this guy to this identity one morphism. So there's a dual sort of notational way to write this. Yeah, there's a question.
Why do we call it evaluation?
The question was, why do we call it evaluation? And I'll answer that in a second when I do an example. But before I do the example, I want to introduce this notation because it will make these equations make more sense. So there's a dual sort of notation for the same picture. I can, instead of, it's sort of a Poincare dual to this picture. Here we're drawing objects as points, one morphisms as one-dimensional things between them, and two morphisms as sort of two-dimensional things. But there's a Poincare dual picture where I think of y as being a region, and I think of G as being some kind of boundary which separates y from x. Maybe I'll shade the region x. Okay. I think of F is a morphism which goes from x to y, so that can be a shaded region with a different kind of shading. It's a new boundary between these different regions. And this evaluation is a morphism which goes from this composite of G composed with F to the identity, which is something which goes from y to y. I might not write the identity. You can do a similar description of the co-evaluation. The co-evaluation can be written in the same kind of string diagram description, but it's going to correspond to a diagram which looks like so, where now we have the morphisms in the opposite order, and we go from the identity to the composite. And then these equations say that this pictorial way of representing these morphisms actually makes sense. So these equations become the following. They say that if you form, let's see if I can do it. So if I right. So if I start with F, so this is my F, and then I apply the co-evaluation, and then I apply the evaluation, that this is the same thing as just having the identity on F. And similarly, the second equation says that if I start with G, which now goes like this, and I apply the co-evaluation on the other side, and then the evaluation, that this picture is, in fact, equal to this picture. So I can straighten out these string diagrams. It makes sense to draw them this way. So a good question is, OK, why do we call the evaluation and co-evaluation? And why do I call it duals? So let me give two different examples of this. So the first example is going to explain why we call it evaluation and co-evaluation. There's actually two different kinds of terminology because there's sort of two examples, two sort of primitive examples which turn out to be just examples of the same phenomena. And they have different terminology, so there's sort of this difficulty with the terminology. So sometimes instead of co-evaluation and evaluation, they're called unit and co-unit. OK. So one example is if you have a monoidal category. So if you have a monoidal category, so for example, vector spaces with its tensor product, its usual tensor product, then you can form a two-category. Call it B-vect. Okay, so this is a two-category which has only one object. The one morphisms are the vector spaces, and the two morphisms are the maps of vector spaces. The horizontal composition is given by tensor product. So we can ask, when is a vector space dualizable? So what would that mean? That would mean that we have another vector space, which we might call X dual. And we have a map, the evaluation, which allows us to pair those two vector spaces. And it goes to the identity morphism on our unique object. So that's the unit object of our monoidal category. So in the case of vector spaces, that's just the ground ring. Okay. Now, any vector space has a dual vector space. But not every vector space has a co-evaluation. So the co-evaluation is a map the other way, going from, in this case, the ground field into the tensor product. And these equations say that element of the tensor product of our vector space and our dual vector space represents the identity map. So you have to be able to represent the identity map as an element in this algebraic tensor product. And that's only true if your vector space is finite dimensional.
Can you make a comment about left dual?
And I made a comment about left dual. So in general, if you just had a monoidal category, this is one of the homework exercises, in fact, there's a difference between left duals and right duals. And in a general bicategory, there's a difference between left duals and right duals. In fact, you know, it's, yeah. And, but in a symmetric monoidal category, there is no difference between left duals and right duals. It's also part of the homework. So I should say left dualizable or right dualizable, but those end up being the same condition in this case. The other key example that is where the two category is the two category of categories, functors, and natural transformations. So in this case, a functor, a one-morphism, is left dualizable if it is a left adjoint. And in particular, part of that says there exists a morphism going the other way in some data. So the morphism going the other way will be the right adjoint to F, our left adjoint. So sometimes dual one morphisms are called adjoint one morphisms. And then the co-evaluation and evaluation are usually called the unit and co-unit when you're speaking about adjoint functors. So this is sort of the primitive idea of dualizability. So how can we, so this actually helps give rise to a theory of dualizability in higher categories as well. So at the end of the lecture last time, I introduced these Seagull N categories. And there are many different versions of infinity N categories that I could have chosen to do instead of Seagull N categories. So you might ask, OK, what are the advantages? Why did I choose Seagull N categories? What are the advantages of Seagull N categories? And for the purposes of, why did I choose them for the purposes of this workshop? Well, there's a couple reasons. So one reason, which is an important reason, is that it's relatively easy to construct examples. And I wish I had more time to construct even more examples. Maybe on the last day we'll see some more. But it's relatively straightforward to construct examples of these guys. Okay, but they're not unique in that respect. Another advantage, which is that it's not quite, I wouldn't say it's easy, I'll say it's possible to compute functor objects, to compute functor Seagull N categories. But the most important reason for our purposes, is that it's easy to extract pieces of the higher category. There's it's almost trivial to sort of extract certain kinds of data from the higher category and look at it and examine it and play with it. So we already saw some examples of that. So if X is a Seagull N category, part of the data, it's easy to construct the Hom Seagull N-1 categories. Part of the data is that you can construct these ABs, okay? Seagull N-1 categories. We also saw that as part of the inductive definition, we were able to relatively easily construct this homotopy category. So out of the Seagull category, we can construct these various kinds of objects. You can do other things. You can then take this guy and you can extract further Hom Seagull categories. So sort of Seagull N-2 categories of morphisms. You can sort of throw out the higher information by applying pi naught at a certain level. There is this pi naught construction. You can apply the homotopy category, to get to homotopy category of one of these ABs. There are a variety of ways that you can just sort of extract off of this object very directly these different categories without going through a lot of hoops in order to access this information. It's sort of right here for the taking. Yeah?
What kind of object is H of X? Is that an N category?
This was just an ordinary one category. The question was, what kind of object was H of X? And this is an ordinary category. There's a similar construction, which isn't much harder, where if you have like a Seagull N category, you can extract a homotopy 2 category out of it. It's easy to extract a 2 category out of a Seagull N category by, sort of playing these games. And in fact, that's a very important thing. So one of the things that we're going to extract from our Seagull N categories, maybe I'll start drawing it here. So suppose that we have a Seagull N category X. That's sort of our basic object. Out of that, we can extract these various kinds of, by doing these kinds of games, we can extract different kinds of 2 categories out of it. So we might be able to extract, for example, we might be able to take the objects, the 1 morphisms, and the 2 morphisms of our Seagull category, and take those up to equivalence by applying a pi naught at the appropriate stage. So this is some 2 category that we've extracted from our Seagull N category. Then we can ask, OK, once we're in a setting where we have a 2 category, we can take our definition of duals and say, aha, we can ask, makes sense now to ask for 1 morphisms in this 2 category to have duals. So this gives us a concept of duals for 1 morphisms, or dualizable 1 morphisms. You can also extract things which look like at the top they have the N morphisms up to maybe higher equivalence than the N-1 morphisms, and then the N-2 morphisms. So from this, you get a theory of duals for N-1 morphisms. They're sort of the middle layer of this 2 category. And you get everything in between. If you look at the N-3, N-2, N-1 2 category, then this gives you a theory of duals for N-2 morphisms. And all of these just depend on these sort of small categories that we can extract from our Seagull N category. In fact, we want to go more. And what we're going to do, we're also going to have a symmetric monoidal structure. And I didn't really say anything about that yesterday. And I'm not actually going to say very much about it, because there are several different things you could try. So, here are some examples are, you could say, OK, spaces are a kind of infinity n category. The sort of the homotopy hypothesis sort of built into this definition. So anytime I have an operad valued in spaces, I can view it as an operad valued in n categories, in Seagull N categories. So then I can ask about algebras for an operad. So one approach to symmetric monoidal n categories would be to say that they're algebras for an infinity operad. Another approach would be to construct a theory of gamma objects. So gamma is a category that's like the simplex category delta, and you have a good theory of symmetric monoidal infinity n categories given by presheaves on gamma valued in infinity n categories satisfying some conditions. Another approach is to sort of invoke the stabilization hypothesis. The stabilization hypothesis. Say that, well, a symmetric monoidal infinity n category should be something where I can deloop it arbitrarily many times in this sense of adding adding points. So you can take sort of the co-limit, or excuse me, the limit of those forgetful functors, and that can give you one kind of notion of a symmetric monoidal infinity n category. And these will all give you equivalent versions, but I don't really care about the details of which one you're going to prefer, because all that we really care about is that we can extract from X the homotopy category of X, and that will be a symmetric monoidal category. Because then we can talk about duals for objects. As long as the different structures that we give would give the same underlying symmetric monoidal homotopy category, then they'll give the same notion of duals for objects. So now let me introduce an important definition that we'll explore. If C is a symmetric monoidal infinity n category, we will say it is K fully dualizable if all objects, one morphisms, two morphisms, etc., all the way down to k minus 1 morphisms. So we have k different layers here. So if there's these k different layers, if they all have both kinds of duals, left duals and right duals. So objects have both left duals and right duals. The one morphisms all have both left duals and right duals, the two morphisms, and so forth. So there are k different layers. And
I'm sorry, maybe I missed something, but didn't you comment that if you have a symmetric tensorial monoidal category, it doesn't really matter which kind you talk about?
for objects.
For objects.
Yeah, for the higher stuff, it still matters. The question was, I had mentioned that for a symmetric monoidal category, there was no difference between left duals and right duals. But that was just for the objects. When you start combining the different layers, it's still true that the objects, if this is symmetric monoidal, there won't be a difference between left duals and right duals for objects. There will be a difference for these different layers. And sort of the really interesting thing that sort of is that when you start combining these different layers of dualizability, each one of these layers doesn't give you a whole lot, but when you combine them, individually, but when you combine them, all of a sudden a rich structure emerges. There's this beautiful connection to topology, and the goal for this course is sort of to understand that in the easiest cases, the low-dimensional cases, completely explicitly as possible. That's sort of where we're going. So just one example of this kind of extra structure which emerges is the Serre automorphism. So here's an example of extra structure. So suppose that this is at least 2 fully dualizable. So we have duals for objects, and we have duals for one morphisms. Then for any object x, I can construct for any object we have a canonical automorphism of x. We have a canonical map from x to x, the so-called Serre automorphism. Goes from x to x. And how do we construct that? Well, first we start with x, okay, which we can view as x tensor 1. Okay. Then we can apply the, later down we're going to apply the evaluation, which goes from x and x dual and combines them to get the unit object. And this is going to be an automorphism, so it's going to land in x, which we also view as x tensor 1. Okay. But because we have duals for one morphisms, this evaluation has a morphism which goes the other way. It goes from the unit to x tensor x dual. This is the right adjoint of the evaluation. There's also something similar where we use the left adjoint. And then we can hook these up by using the fact that we're in a symmetric monoidal category, so we can swap these 2 copies of x. And this defines for us a morphism which starts at x and ends at x. It's sort of canonical, as canonical as this dualizability data is, for any x. So there's some homework problems which have you explore a little bit of the properties of this. And tomorrow we'll really explore a lot more about the Serre automorphism. The rest of today, I want to sort of, so there's sort of, let me explain the plan. So tomorrow we're going to explore what happens when you have sort of 2 layers of dualizability and how they interact, especially when we sort of increase the category number to 2 and to 3. We'll talk a lot about the Serre automorphism. On Friday, we're going to talk about what happens when you have 3 layers of dualizability and how those all come together and form this very, very neat structure. And today, the rest of today, I want to talk about just the 1 layer of dualizability. And I want to talk about the cobordism hypothesis, which motivates and explains all of this structure. And so hopefully it'll be very explicit and enjoyable. So let's see. So to do that, though, I need a way for us to get a real concrete handle on the bordism category. Okay, so the question was, what does this script R on top of the evaluation map mean? So it means that the evaluation script R is the right dual of the evaluation. So I'll write that over here because that's it's important. So V is the the right dual or right adjoint to the evaluation. So if you think about this little box, the evaluation is a one morphism which goes from the tensor product of x and its dual to the unit object. The adjoint is a morphism, the right adjoint is a morphism which goes the other way. For further evaluation and co-evaluations between the evaluation and its right adjoint, sort of higher evaluations and co-evaluations.
Can I just ask? It has a right dual because it is left dualizable. That's the way it's
you have to choose whether, say, it's right dualizable or left dualizable, and I'm fairly convinced that there's no good way to make that convention that satisfies, at some point there'll be some place where you're like, oh, this is backwards to how it should be. It's just impossible. So, yeah. You can say has a right dual, but so there probably is a way I could have avoided it here, but yeah.
So if I if I believe the homotopy hypothesis, and I take a space and think of it as an infinity zero category, I see. I would need to have some kind of multiplication on it before I could ask whether it was, fully dualizable, right?
Yes. So the statement was, if C was a space thought of as an infinity n category, the statement was, yes, you would need a multiplication before you could ask about this definition. And then you're,
okay,
was that?
I guess my question doesn't.
That's it? Okay. So, okay. How are we doing? Perfect. Okie dokie. So now I really want to compute something fun. So okay. And to do that, I'm going to work with just one. We're going to put higher categories on hold for a second and just work with symmetric monoidal categories. So everything I'm going to say is just going to be about symmetric monoidal categories, unless I say otherwise. So to really get a handle, we need some way to kind of understand the bordism category. So I'm going to invoke some results which you could, for example, you could prove it using some techniques that came from my thesis, but there are other ways to just do it. It's not too, I think it's a believable thing that I'm about to say. So you can look here. But this is a theorem that I'm going to use. So this is going to be a one category, the symmetric monoidal one category of bordisms, one-dimensional bordisms, which are oriented. So this is the symmetric monoidal category of zero-dimensional manifolds and one-dimensional bordisms, which are oriented. It's something that we've seen in other lectures, at least for higher n. So the theorem is that this category has the following presentation as a symmetric monoidal category. So first there are some generating objects. So the generating objects, there are two of them. There's a plus point and there's a minus point. And any other oriented zero manifold is a disjoint union of these plus points and minus points. So these generate everything. And then there's generating one morphisms. And you only need, besides the ones that you get just from the fact that you have a symmetric monoidal category. So the fact that you have a symmetric monoidal category says that, well, if I take a disjoint union of 6 copies of the plus point, then I can permute them by the symmetric group. In addition to those, you need 2 additional bordisms. One which pairs the plus point and the minus point together, and another one which goes the other way, pairs the minus point and the plus point, just sort of a co-pairing, like so. And then there are, and that's it. That's all you need to build everything. But there are some relations. There are 2 relations. And if you start with a plus point and form the following cobordism by gluing on these 2 guys, this is the same as the identity on the plus point. And conversely, if you start with a minus point and build this cobordism, that's the same as the identity there. So this means that if you have any other symmetric monoidal category, then functors, TQFTs, oriented one-dimensional TQFTs, are determined by, and in fact are the same thing as giving the values of these generators subject to the requirement that these relations hold. Yes.
It's a similar kind of thing happened with categories.
I'm sorry. Well,
Categories?
Sorry, what was the question?
Well, so your answer to my first question is yes. Yeah. So I want to know, can you do it for higher categories?
Yeah. So the question was, is there a free symmetric monoidal category, and can you do it for higher categories? And the answer is yes. You can do. There is a free symmetric monoidal category, and generated by another category. And you can do it for higher categories. This is not of that kind because, unfortunately, the sort of generating one morphisms, their sources and targets are not things that we started with. They're sort of consequences of the generating one morphism. So it's sort of an iterated construction where you start with a 0 category. You take the free guy generated by it. Then you sort of attach some cells to that by specifying new one morphisms whose boundaries are something that were consequences of the 0 category you started with. And you can keep adding more and more. So it's kind of like a presentation is kind of like a CW structure for a higher category. In this case, you get a, and just like for CW structures, they have a really good property, which is that for mapping out of them, you just have to see where, just have to determine the map on the cells subject to the attaching maps, and maybe if it's truncated in some way, there's some relations that you have to check. So as a corollary of this, if you look at functors, symmetric monoidal functors from board 1 oriented into any other target, this is equivalent, you just have to a category whose objects are just specifying these data, so which consist of an object x, the value of the plus point, an object x bar, the value of the minus point, an evaluation and a co-evaluation. So functors from the bordism category to C are exactly sets of dualizability data, or equivalent to a category of dualizability data. And this is equivalent as part of the homework exercise. So this is problem 1.2. You show that this is actually, you can take your symmetric monoidal category. You can look at the dualizable objects. Then you can take its core. You can extract the maximal groupoid. So it's a maximal groupoid of dualizable objects. So functors from the bordism category, and more of this equivalence is given just by remembering this value. So functors from the bordism category to any symmetric monoidal target category are the same as dualizable objects. In fact, the functor category is this groupoid of dualizable objects. So that's a statement which goes under the name of the cobordism hypothesis, that and related statements. So and this is motivation for most of the material here. So roughly what the cobordism hypothesis says is that if you look at the bordism N category, the framed bordism N category is the free symmetric monoidal, well, a good proper version of it will be the infinity N category, generated by a single N fully dualizable object. So a version of this was proven in my thesis for 2 categories, not for infinity 2 categories, but for 2 categories. A better version was proven for infinity 2 categories by Mike Hopkins and Lori Jacob, and then that led into a beautiful, beautiful proof for all n, which is now you can read an expository account of that on the archive, or talk to Jacob since he's here. So the framed bordism N category, as a symmetric monoidal infinity N category, satisfies this property in the precise sense that functors, symmetric monoidal functors from board N framed into any other symmetric monoidal infinity N category are equivalent to, well, first you take the maximal fully dualizable subcategory, N fully dualizable, and then you extract the core. So this is the maximal infinity groupoid, or space. So the statement is that the framed TQFTs, a fully extended framed TQFTs, are the same as fully dualizable objects. They're determined by the value of the point, which is a fully dualizable object.
Is there a reason why it's a groupoid instead of?
Yes, there is a reason why it's a groupoid, and that's for n equals 1. I think that's maybe part of this homework exercise. If not, it's a great exercise. And maybe I will talk about on a different day the higher version of that, but I might not. It's not too hard to work out why it's a groupoid. It's sort of a corollary of the n equals 1 case. So that's, and it really comes down to asking, okay, what are the morphisms of these tuples? Can you have an arbitrary morphism of tuples like this? The answer is no. If it's really if it's really natural in respect to x and x bar, then in fact it has to be invertible. That's the crux of the argument for the n equals 1 case.
So if we want everything to be fully dualizable, you need every morphism to have a dual. But if you take the groupoid, they already have an inverse. Don't the inverses are already dual?
So inverses, so a map which is invertible has a dual, namely the inverse. And it has both kinds of duals. And since the inverse also has inverses, it has both kinds of duals. So invertible things are in the fully dualizable object, at least if the source and target are also fully dualizable. Now, so what this is first you restrict to the fully dualizable category, and then you throw out the non-invertible morphisms. So you have, if you do it in the opposite order, if you first look at this, the maximal space, then you'll get into trouble. You'll actually throw out way too much. You look unhappy.
Isn't the functor specified by its value on the point? And it has to be a fully dualizable object and the rest. Why do you need the K? What I'm asking.
Well, this is a statement which is saying that if you had two different functors, you could a priori, because we're in an infinity n category world, you could have a non-invertible maps between those functors. But that doesn't happen. It's actually, they're always invertible. That's the
Maps between the functors.
The maps between the functors are invertible. So okay. So one thing that you have, and this is sort of a general principle, anytime you have a mapping object, like functors from the bordism category to some other category, then whenever you have maps from B to C, then the automorphisms of B act on this object. In fact, anything which acts on B acts on this object by precomposition. So the orthogonal group acts on the framed bordism category. So these are bordisms equipped with a framing of their tangent bundle. So this acts by changing the framing. So it acts on this. So it acts on the space of fully dualizable objects. At least that's what you would learn if you had the cobordism hypothesis on hand. Well, I'm lying a little bit because this is only an equivalence, and so to pass the action through an equivalence is sort of a coherent homotopy action. That's sort of a technical detail at this point. And there's a second part to the cobordism hypothesis. So you can build lots of different versions of the bordism category. So if you have a group mapping to the orthogonal group, then you can consider the map of tangent spaces, the map of classifying spaces. And if you have a manifold, you can, a manifold has a tangent bundle, which has a classifying map to BON, and you can ask for a lift to BON. So lots of structures arise this way. Orientations arise when G is taken to be the special orthogonal group. Spin structures arise when it's the spin group. Lots of different things you can put there. So you might be curious, not in these framed bordisms, but in functors from board G and into C. And fortunately, Jacob proves for us a version of the cobordism hypothesis, which is valid in that setting as well. So first you look at this space of fully dualizable objects, and then you take the homotopy fixed points. You have this induced action of ON, so you have an induced action of G, and so you can take the homotopy fixed points. So that gives you a way to attack all kinds of TQFTs. So if you're interested in TQFTs, you should be interested in fully dualizable categories and interested in this ON action. And that's sort of where what we want to do. We want to try to look at a category, maybe a low-dimensional higher category, like dimensions 2, 3, and really understand how, just from having dualizability, how you could get an O2 action, an O3 action. Well, let's look at this case again. Let's see, where do I? This is the one-dimensional bordism category. So the one-dimensional bordism category is supposed to have an action. You know, framings in dimension 1 are the same thing as orientations. So this is the framed bordism category in dimension 1. And an action of O1 is the same thing as an action of Z mod 2. So do we have that action? So what would that mean? That means for the non-trivial element of Z2, we have a functor from the bordism category, the oriented bordism category, to itself, a non-trivial functor. And in fact, we can use this presentation to see that, yeah, we do have such a functor. What we can do is we can take this object plus, and we can map it to the object minus. We can take the object minus, and we can map it to the object plus. We can take this plus minus cobordism, and we can map it to, well, now it has to go from minus to plus, and there's a cobordism which does that. And similarly, we have a minus plus one which goes to something similar. And a little calculation shows that this is in fact order 2, and in fact it's a Z2 action. So we have a Z2 action on board oriented. So another way to formulate this mapping property, this is equivalent to saying that, well, then board G, N, we should be able to obtain that by taking the bordism category, the framed bordism category, that's the thing which spits out this space, the thing which has an ON action and hence a G action, and forming the homotopy quotient, taking the quotient by the G action. And so that's what we should expect here, is that if we take the quotient by this, then we're getting a manifold where the structure, let's see. So let's look at board. We're going to look at board 1 oriented, where we take the homotopy Z2 quotient, the homotopy quotient of this. What is this supposed to be? Well, it's supposed to be board, what I wrote as board O1, 1. That's what it's supposed to be. So what is this? So what is this structure? Well, our manifolds are equipped with a tangent bundle, and then we need a lift. Well, that's no data. So this is just the unoriented bordism category. So there's a similar result about the unoriented bordism category in terms of a presentation. So it also has a presentation. Yeah, so let me repeat what I just said. So in order to have this mapping property, this guy has to be the homotopy quotient. So if that's true, if that was true, then that means that, we're saying that, let's look at the case that G equals O1. So the case G equals O1 should be this homotopy quotient. And I'm just recognizing that the case G equals O1 is what we would usually call the unoriented bordism category. So this is the identity map, right? This is equality here. So there's no data in a lift. So it's just manifolds. It's just manifolds with no additional structure. So what I'd like to explain is how we can actually prove this for not for infinity 1 categories, but just for ordinary 1 categories. We have this explicit description of the bordism 1 category, the oriented one. We have this explicit Z2 action. I'm about to write down an explicit presentation. So it has generating objects. Well, there's only one unoriented point. There aren't. Every other unoriented zero manifold is a disjoint union of this one unoriented point. It has a generating morphisms. Well, there are two. But now they pair and co-pair this unoriented point. And then there are some relations. So the relations say what they did before. This is equal to that, which is also equal to this. But then there's a new relation, which is that if you take this cap and you twist the ends, that's the same thing as that. You might object that, oh, there should be another one for the other cap, but that's actually a consequence of these relations. So now I want to take the homotopy quotient of this Z2 action. Maybe I'll do that over here. So the usual way that you take a homotopy quotient for spaces as well. You take your space. It has an action by G. So you can take the product with EG. Now it has the same homotopy type as X, but now it has a free G action. And then you take the quotient of this by G. So now we want to do this in the world of higher categories. And we want to do this in the world of symmetric monoidal higher categories. So the first thing is, what is an analog? Right over here. So an analog of EZ2, well, in the world of categories, there's an easy one to describe, which will be very nice for our purposes. There's this category J, which is the free walking isomorphism. So it has two objects, J and J inverse. And it has two different morphisms, which are isomorphisms. And it has no non-trivial automorphisms. So it's this category. So J is equivalent to the terminal category. But J has a free Z2 action. So if we were in the world of just ordinary categories, now we could form the homotopy quotient. We're not quite in the world of ordinary categories. We're in the world of symmetric monoidal categories. So we have to be a little bit more careful. So given the symmetric monoidal category C, I'm going to define a new symmetric monoidal category, tensor with J, and it has the following property that functors, symmetric monoidal functors from C tensor J into D are the same thing as ordinary functors from J into symmetric monoidal functors from C into D. So proving this thing exists is very similar to proving that there exist free symmetric monoidal categories generated by ordinary categories. And in the case of the bordism category, we can get an explicit description of this. So make sure I do this right. Yep, OK. So this is going to has a presentation where the objects are pairs. It's sort of freely generated as a symmetric monoidal category by pairs which look like an object in the bordism category, maybe I'll call it B, and an object in this J, maybe I'll call it J. Okay. And morphisms, which look like pairs of morphisms. So maybe I'll say that they look like a morphism from B to B prime, comma, the identity on J. Or they look like the identity on some B and then a morphism from J to J prime. Or there's a morphism which says that if we take B and J, and we take B prime and J, then there's an isomorphism between that and B tensor B prime and J. So if we have the same J, we can collect terms. And then there are some relations. The relations are those in the bordism category, the relations in J. The relations are that these two kinds of things commute, and that if we take B, J, and B prime, J, and we combine them to get B tensor B prime, J, and then we braid them to get B prime tensor B and J, or we braid them and then combine that commutes. So these relations are not hard to work out. They're just sort of unraveling the consequences of this property that you want it to have. And now we can take the homotopy quotient of this guy by looking at this category, which now has a free Z2 action because it's free on the J factor, so it acts sort of the same. And just taking the ordinary, the sort of naive quotient by Z mod 2. So this is a thing which has objects which look like equivalence classes of a bordism and an object in this weird category J. But we can combine this with the presentation we already have, so we can get an explicit presentation of there might be some relations that I'm forgetting with the identity objects. You're right. There should be some stuff about the identity objects. I'm going to neglect that for time. it's probably a good exercise to work out what I was forgetting. OK, so this board's got to go. So combining that presentation with that, we get that board 1 oriented homotopy quotient looks like the following. So it has generating objects plus and minus, which we think of as sort of plus is sort of equal to the equivalence class plus my favorite object j. OK, this is the same thing as minus and j bar. And minus is sort of shorthand for minus comma j. So we sort of have notation for writing everything with just j. So we have sort of the morphisms from before. We have this sort of oriented morphism, which goes like this. We have another morphism, which goes like this. And then we have 2 more morphisms. So where do these come from? Let me do it first at this sort of level here. So if we have an object x, we have our j, well, then we have this morphism which looks like the identity on x, comma, the unique morphism to x, comma, j bar. But in this quotient, that's the same thing as x bar, comma, j. So that means we have a morphism which starts off at the plus point, and it goes off, and it ends at the minus point. So in the middle, you can think about this as a bordism, which has a kind of defect in the middle, a disorientation, a place where the orientations mismatch. And there's another one which starts at the minus point and ends at the plus point. And you have relations. So you have relations which look like this, where this is plus and plus, plus and plus, etc. You also have the fact that these two, these are inverse. And then you have one non-trivial relation, which looks like the following. It says that if we start with a minus and we disorient ourselves and then apply this bordism, this is a pairing between minus and minus, that's the same thing as first disorienting ourselves the other way and oh no, the same way, and then ending up here, the minus guy. OK. So now that we have this, we can see, aha, there's a clear functor from this guy to the unoriented bordism category. We just take both points to this guy. We take these guys to this guy. And we take these two guys to isos, and all the relations that are supposed to hold. So we get a functor from this homotopy quotient to the unoriented bordism category. And you can now check. It's an exercise. And it basically follows from problem 2.3. Problem 2.3 is a hard part. It gives you a way to check when a map of symmetric monoidal categories is equivalence. Once you have these presentations, you can just check that, yeah, this, in fact, gives you an equivalence between these two directly. So I'm out of time. So that's it for today.
Any questions?
there any way to check that without using presentation? I mean, it's okay to use something about J.
Is there any, sorry, what was the question?
So if you do not use presentation of bordism categories, you directly think of them as category of bordism, like geometric axioms, then can you check that?
The question was, if you don't want to use the presentations of the bordism category, if you want to just do it directly, can you see this? And I'm not sure. It probably depends on exactly how the details of how you set up what the bordism category is, because there's a couple of ways you could imagine of doing that. Having the presentation sort of reduces it to like this combinatorics question. It's maybe not the most natural thing. You might say, well, let's just do it. So I'm not sure. I think you can probably, at least if you had a good model for the homotopy quotient, then you should be able to just do it.
Other questions? Well, if not, let's think to speak again. Coffee, tea, and food available upstairs.